Next talk is by Debabrata Deb, and he will tell us about the effect of anisotropy in highly magnetized white dwarfs.
Good evening everyone, and thank you for this opportunity to present my work in this event. So the work I am going to present today is titled as Studying the Effects of Anisotropy on the Highly Magnetized White Dwarfs in General Relativity. And by magnetized white dwarf, we are going to basically focus on the super Chandrasekhar white dwarfs and study the effects of combined effects of anisotropy and magnetization on the super Chandrasekhar white dwarf. And I am going to tell you later what is actually super Chandrasekhar white dwarf. So last day actually Manjari discussed the evolution of the stars, and she has actually focused in the lower panel where the star is the main sequence star has large mass above 10 solar mass, and how it is actually actually reach to the end phase of neutron star or black hole. So for the totality I am going to present the upper panel evolutionary phase for the stars, where the mass of the star is less than 10 solar mass. Then actually what happens when the fusion of the hydrogen just tends to end, then the star actually increases to the red giant, and when it reaches to the red giant, at that time the helium fusion happens to produce the oxygen and carbon, but the mass of the red giant is not enough to provide the temperature at the core to again fuse the carbon and oxygen to having the fuel for the star, and as a result the red giant actually removes the outer layer by forming the planetary nebula, and it leaves behind some carbon core, what is actually white dwarf. So white dwarf is actually some star which is supporting the extreme inward gravitational pull by the degenerate electron gas pressure. So note that I am saying here the white dwarf is made of degenerate electron gas. This is because we are considering there is no strong interaction like neutron star here, and electrons are mostly not interacting by themselves, and we are considering them as a simple gas. So in 1935, in his seminal paper Chandrasekhar, this is actually the picture of the Chandrasekhar paper. In Chandrasekhar actually employed the equation state for the electron, where he has applied the Fermi-Dirac statistics, and immediately one have the number density for the electron, and by applying the simple technique of statistical mechanics, one can have the energy density and pressure. So you have the equation state for the electron. Now applying the force balance equation and the mass balance equation, you can have the, obviously this is the Newtonian regime, not the general relativistic effect has not been considered at that time. So Chandrasekhar arrived to the mass radius relation for the white dwarf, and there is an interesting part. You can see that if you consider n equals to 3, then the mass of the white dwarf becomes independent of the central density, and it arrives into the limiting mass for the white dwarf, which is the 1.4 solar mass. So let us now discuss what is supernova. A supernova is an extremely luminous stellar explosion that involves disruption of actually the entire star, and it is so much luminous that it is almost 10 to the 10 times luminous compared to the sun actually. So there are actually majorly two type of supernova are there. Type 1 supernova, type 2 supernova. So type 1 supernova event can be classified into 3 parts: type 1a supernova, 1b and 1c. So type 1b and 1c actually reduces into the black hole, whereas the type 2 supernova reduces into the neutron star. And note that all these 3 types of supernova are actually core collapse supernova. Whereas we are more interested about the type 1a supernova, which is actually the results from the thermonuclear explosion of the carbon oxygen white dwarf when its mass actually approaches to the critical mass limit, that is the 1.44 solar mass. So why I mean even astronomers are more interested about the type 1a supernova because of their unique characteristic of light curve. So in the left hand side plot you can see the light curve for the in the plot in the left hand side you can see light curve for the different type 1a supernova, and based on the luminosity the decaying is happening. So for the higher is the luminosity, decay rate is less for the type 1a supernovae for those cases, and this is actually Phillips relation. And if you apply time scale crunch factor, you can actually merge into a unique characteristic for the type 1a supernova. That's why it is actually treated as standard candle or standardized. They can be made as a standardized candle. And this standard candle has I mean, there is a significance of it, how we are presently looking at the universe nowadays. Why so? So let me discuss that. So before that, if you know luminosity of a source, absolute luminosity of a source, then you can easily derive the distance of the luminous object by applying the inverse square law. So type 1a supernova, that's why actually considered as a standard candle, because it has remarkably similarity in brightness, which can be, as I said, standardized in considering the distance between the observer. So 24 years ago, the Sol, two team led by respectively Sol Perlmutter and Brian Schmidt, they actually declared that the expansion of the universe is accelerating, which is a Nobel Prize winning discovery, and it immediately leads to the presence of the dark energy, which is now widely accepted. And the one of the basic assumption behind this work was they have considered type 1a supernova as the standard candle. And one may again ask what is the reason behind the such enormous luminosity of the type 1a supernova. This is because of the radioactivity of the nickel 56, which again decays into cobalt and then iron, these two reaction to decay into cobalt and iron, for these two reaction the half time is basically 7 days, 6 days and 77 days, which actually shows what is the length of the this light curve width. So these are the all reasons why actually type 1a supernova has been considered as a standard candle. But the problem arises like this. Immediately recently it had been seen that there are some overluminous type 1a supernovae and underluminous type 1a supernovae. So I am just trying to focus on the overluminous type 1a supernovae. So you can see from this plot, the supernovae within the circle is basically highly overluminous, and they are not following the Phillips curve, what the usual type 1a supernovae should follow. And the luminosity is actually related to some mass energy and the kinetic energy of the ejecta velocity. But it has been found that for those cases ejecta velocity is very low. So entire luminosity is coming from this mass energy thing. And further it has been seen that the nickel mass found for this type 1a supernova is as high as 1.8 solar mass. But normally it can be seen for the normal type 1a supernova, the nickel mass critical limit should be like 0.85 solar mass. So you can see the nickel mass is much higher for this peculiar type 1a supernova. And if you just try to predict what should be the mass of the progenitor white dwarf, it should be as high as 2.8 solar mass. So it becomes, this is really a setback to the community. So this is known as actually super Chandrasekhar white dwarf. So immediately researcher came with two competing model, merging of massive white dwarfs and explosion of rapidly rotating white dwarfs. But both two scenario failed to explain the highly massive 2.8 progenitor white dwarf. And later Mukhopadhyay and collaborator actually came up with a solution by introducing magnetic field. They able to show that they can explain such highly massive progenitor white dwarf. So it is difficult from observation to tell what is the magnetic field inside the star, and so it requires some theoretical model to tell the strength of the magnetic field and how it affects the physical parameter of the magnetic field. So again there it can be found that the magnetic field inside the white dwarf can be as high as 10 to the power 14 Gauss, as shown by this researcher. So now it can be seen that Chu et al. Has been shown that using the orientation of the magnetic field, it can be solved whether maximum mass of the compact star is rising or decreasing. And by magnetic field orientation, they mean that when the magnetic field is along the radial direction, it is radially oriented, and when it is along the transverse direction, it is transversely oriented. Although they have introduced this idea, but they failed to explicitly discuss all these things and introduce in the force balance equation and to study what the effect of magnetic field and if there is anisotropy due to the magnetic field and its orientation on the compact star. So in our work, we have actually applied this idea of magnetic field orientation and actively, and further we have assumed an important idea, that is we have considered that anisotropy is arising due to both local anisotropy of the fluid and the presence of the magnetic field, and we are going to see that it will play a crucial role for the magnetized compact star, for the stability of the magnetized compact star. So now if you consider a isotopic system, the stellar structure equation looks like the equation 1, where the left hand side term is the hydrodynamic force, the first right hand side term is the gravitational force, and the red term is the anisotropy due to the magnetic field. So if you consider isotopic system, the anisotropy comes due to the magnetic field as you can see as the red term. So at the center, when you consider, so at the center you can see that anisotropy is proportional to the magnetic field, but at the center the gravitational force and the hydrodynamic forces are 0. But the anisotropy force is not 0, as a result it immediately disbalances the stability of the system. So to resolve this issue, we have actually considered the anisotropy is made of, anisotropy has combined effect due to anisotropy due to the matter and anisotropy due to the field. And considering this the effective anisotropy due to fluid and matter, we are able to resolve this issue. I am quickly skipping all this for the less time. So we have considered the equation state like this as shown in equation number 6, and to bound the system we have considered a functional form for the magnetic density dependent magnetic field profile, considering Bandyopadhyay et al. And based on all this, we are able to solve the TOV equation for our case, and you can easily see that we are able to show a stable stellar structure equation for white dwarf, where using anisotropy due to both the magnetic field and fluid, we are able to explain the 2.8 solar mass higher the progenitor mass, and for the transverse orientation, and for the radial orientation we can also able to explain the lower mass compared to the 0 magnetic case. So another interesting thing is like for the radial orientation, based on the chosen different parametric value, we are able to explain the different set of sub, super and standard Chandrasekhar white dwarf in a single mass radius curve. And you can see different combination there, like the sub and standard, sub and super, and the standard and super Chandrasekhar white dwarf. So through this work, so we are able to solve some important aspects, and this is the take home message like this. Using the combined effect of anisotropy due to fluid and magnetic field, we are able to show that for the magnetic field, it is essential that you need to consider combined effect of anisotropy due to fluid and magnetic field. Also, our work has shown that we should be cautious about considering type 1a supernova as considering standard candle. Obviously, it has a significant implication on the modern day idea of the cosmology and so. And obviously, another thing we are able to show that based on the choice of the free parameter, we can accommodate all the combinations sub and super Chandrasekhar and standard Chandrasekhar white dwarf in a single mass radius curve. So, all of this, thank you for your attention. And this work has been published to FJ, and I am grateful to the co-authors, Bani and Fridolin, for their significant contribution. Thanks.
Thanks a lot, Debabrata, for this nice talk.